Hi guys, welcome back for another data analysis video. So this is another one-way repeated measures ANOVA video. So I'm going to conduct a one-way repeated measures ANOVA with post-hoc tests again in this video. So a further example of how to do that. This is the last one I'm going to do. I feel like I've done repeated measures ANOVA to death. Now I've demonstrated how to conduct this, including checks of assumptions and post-hoc tests. A few different ways with different data sets, and this is going to be the last one that I will do. So the data I'm going to use here in this particular example is simulated, and hypothetically it relates to sort of reported pain levels experienced by patients at 3 different time points as treatment maybe for some sort of injury progresses. So a patient's had their, in theory, a patient's had their pain level measured at time 1, and then after some treatment at time 2, and then after some more treatment at time 3, and we're looking to see if there's a difference between those time points as to what their reported, self-reported kind of measure of discomfort and pain is. So these are self-report scores on a scale of 0 least pain to 60 extremely painful. That's kind of quite a large scale. So what I'll do in this analysis is I will import some data, then conduct Morchley's test of sphericity, then conduct an ANOVA, fit an ANOVA model. And this time what I'll do is I'll use the I'll use the statsmodels ANOVA RM method, and then I'll follow that up with appropriate post-hoc tests if that's necessary, and hopefully I'll then interpret the results. So I'm going to import some software libraries, NumPy, pandas. I'm going to import from statsmodels.stats.anova. I'm going to import ANOVA RM, so the repeated measures ANOVA method from statsmodels. And I'm also going to import pingouin, because I will use pingouin for the pairwise comparisons, because it's kind of one of the most convenient ways to do your post-hoc tests when you're using Python. So this data frame, as I mentioned, idea is patients are reporting their pain at 3 different time points after treatment of some type. So it's saved as a CSV file on my computer. I'm going to import it using the pandas read_CSV method, and I'm going to save it as an object called pain_df. So pandas data frame object pain df essentially. So if I run that and we look at the header, so the first 5 lines of data, you can see here we've got like a participant ID, time_1. So the other 2 categories are time 2, time 3, and then some pain level on a scale of 1 to 60. So let's, having imported that data, let's kind of first look to see if it meets the assumptions of sphericity for conducting kind of a basic ANOVA test. So I'm going to use the pingouin sphericity method to test for Morchley's, or to run Morchley's test of sphericity. So it's the syntax, which is pg.sphericity, and the arguments or parameters you need to pass are data, which is our pain data frame, pain_df, the dv, which is pain, this numerical pain scale variable, subject, which is this participant column here. So that's just an ID reference number for each participant. We need that so we know which scores belong to which participant, because they're contributing multiple data points in this data frame. And our within equals time, so that's the repeated measures grouping factor, so time 1, time 2, time 3. Let's run that, and what we see is we get a Morchley sphericity. It tells us it gives us a Boolean value, sphericity equals true. So it's telling us it's true that we can assume sphericity for this data set that we haven't violated. So remember, the null hypothesis for a test like this, like Morchley's test of sphericity, is that there isn't a difference, that the data does not violate the assumption of sphericity. If we get a significant result, then it's telling us that it does. In this case, it's telling us true that our data doesn't violate sphericity, and we get a Morchley's omega value of 0.92, chi-square value of 1.14, 2 degrees of freedom, p-value of 0.56. So we can see we've got a non-significant result looking at that p-value using a threshold of significance of 0.05, about 5%, 1 in 20. So it's much above that. So we're probably safe to assume sphericity for this set of data that we're using here. And we do not necessarily need to conduct a robust ANOVA test with some sort of adjustment of the p-value. Sorry about that. I'm going to have to just change that typo because I spotted it. All right, so we're safe to. It's probably okay to use this data for some sort of ANOVA model that assumes that the beta meets the assumptions necessary for a parametric statistical test. And I'm going to use the statsmodels ANOVA RM method. Okay, so firstly, I'm going to create as I've demonstrated previously how to use statsmodels to run this type of model. But what we're going to do is create an object, first of all, specifying the model, the parameters for the ANOVA method, and then we're going to fit the model essentially to this new object we create to get our results, and then we'll just use a print statement to print the results essentially. So I'm creating this new model AOVRM, so that's just an abbreviation I've made up, ANOVA repeated measures essentially, and that's equal to the ANOVA RM method, and I'm passing in our data frame. So the first parameter there, the first argument is pain underscore df. I could have probably typed data equals pain df here. I didn't need to. You can do it without, so it just demonstrates. And I could have also specified dv equals here, but I didn't need to. I could just put the parameter name, which was pain. Remember, this is it's in the single quotes, so it's a string object in Python, and it's spelled exactly the same, all lowercase as it is on the data frame. So Python knows where to extract that from. If we'd have spelled this differently, if I'd have put a capital P here, it'd look in the pain df data frame object, and it would return an error message saying can't find that variable essentially. Participant is obviously our ID number for each participant, and the within factor is equal to its time. And in this case, I've passed it in brackets as a list. Okay, so it kind of gives you some indication that you could, if you can pass in a list, you can pass in more than one. We're just using one independent variable in this case, which is our grouping variable time 1, time 2, time 3. But you could have a factorial design where you pass more than one independent variable in, so worth keeping in mind there. And we'll come on to that. I'll come on to that in the next few videos as well. And then I'm creating this new object called res for results, and basically I'm taking this ANOVA RM object and using this dot fit method. Okay, so I've done that in 2 steps. I've said before I could probably have missed this second line out here. I could probably not bother with that and just put dot fit at the end here with the parentheses, and that would have done the whole thing in 1 step. But I was just trying to be methodical in doing it. And then I'm going to use this print statement. It's a keyword or a reserved word in Python, print, and I'm passing in the res results object. So if I run that, it gives us this ANOVA table from statsmodels. So we can see we've got an F value for our independent variable time, 38.87 if we round that to 2 decimal places. It gives us our degrees of freedom, 2 and 28, which we would need to report when formally reporting our ANOVA, and it's given us a p-value to like 4 decimal places, and that's not going to be exactly 0. But those decimals could go on for a while, and it's rounded to 4 decimal places in all cases here. So what we would do is specify that this was p is less than 0.001. Okay, so what we're seeing here then is we've got a statistically significant F value. So there's a significant difference between reported pain level between these different time points, time 1, time 2, and time 3. But we don't know which levels are different from which. So we don't know if time 1's different to time 2 significantly, time 1's significantly different to time 3, time 2's significantly different to time 3. So we've got these these three pairwise comparisons we need to make. So we need to follow up this kind of omnibus ANOVA test with post hoc tests, comparing all levels of the independent variable time. Yeah. So in this case, what I'll do is I'll use Bonferroni corrected pairwise comparisons to control for the family-wise error rate. Let me just change that. Excuse me. To control for the family-wise error rate, or the likelihood of making a type 1 error when you're making multiple comparisons. So what I'm going to do is I'm going to conduct these post-hoc tests using Pingouin's pairwise underscore test method. And before I do that, though, I'm going to obtain some descriptive statistics for each level of the independent variable separately. So I want descriptors for time 1, descriptors for time 2, descriptors for time 3, because they're going to be useful. They're going to be useful to have to hand to help us interpret the results of the post-hoc tests. Okay, so in order to do that, I'm going to obtain some mean scores for each level of the independent variable. So what I'm going to do here is I'm going to create a new object called time1. I'm going to use the pane data frame and this .loc method. So it's going to locate observations in the pane data frame that that are within the time variable and are exactly equal to time 1. So what this essentially means here is that we're going to extract all of the time 1 observations and save them in this new object called time 1. Okay, all the observations that relate to time 1. So if I run that, and that will return. So we've got 14 objects. They're essentially the first 14 lines by the looks of it. And we're going to do the same because this is a repeated measures design. And we're going to do the same for time 2. And that should be the next 14 lines, funnily enough. And then the same for time 3. So all I'm doing is I'm using this .loc method, which I believe is a pandas method. And we're saying, look in the pane data frame, look at the time variable, and extract everything that is exactly equal to time 3. And that's what we've got here. Right. Okay, so what I've now got are 3 objects, each containing only the observations for time 1, for time 2, or for time 3. Okay, so then let's get some descriptors. I'll use the .describe method here. So time1.pane .describe. If we do that, we see we've got a mean of 47.40. It gives us this kind of 8-number summary, which is useful if we want to know other things such as the median, the min, the max, the standard deviation, things like that. All I'm really interested here is the mean for each of the groups, but I'm using the describe. I could have just used .mean instead of .describe, but it gives us some more information. And what I'll do now is to sort of extract those so we can see them side by side. I'm going to just create some print statements here. I'm using an F string. I'm going to print the text time1 mean, and in these curly brackets, I'm basically going to do a similar thing to what we did above here, using the describe method. Just use the mean method and round it to 2 decimal places. So you'll see what this does if I ran the wrong cell. There we go. So you can see more convenient to look at these side by side. So we can see time 1 has the highest mean, 47.40. Time 2 has the lowest mean, 34.13. So knowing we have a significant ANOVA model tells us that at least time 1 and time 2 are going to be statistically significantly different from each other. And then time 3 has a mean of 38.07. So it's higher than time 2, but it may not be significantly different, statistically significantly different. And that's what we need our post-hoc test to tell us, essentially. Okay, so let's kind of conduct those post-hoc tests using a Bonferroni correction to compensate for the fact that we're making multiple comparisons. And we're going to use the Penguin pairwise underscore test method. So I'm going to create this object post-hoc results post underscore res, and that's equal to Penguin pg.pairwise underscore test. So the Penguin pairwise test method. The data is our pane data frame. The DV is pane. Our within subjects variable, our repeat measures variable, that is the time variable. So group time, group 1, group 2, or group 3. Our subject factor is participant or variable. So that's the participant ID number to allow for the fact that participants contributing more than one data point in this data set. I've set the parametric parameter to true. I'm using a Bonferroni adjustment for the p-value, so a Bonferroni correction. And remember, all that is we take 0.05 if that's our standard or our conventional threshold for statistical significance, and we divide it by how many pairwise comparisons we're making. So we're doing 3 tests in this case. So we divide 0.05 by 3. That would mean we don't accept anything as significant that's as a significance value of less than something like 0.012. It would be, I think. In this case, the adjustment's going to be made, and it's going to demonstrate, it's going to show us anything less than 0.05 that's adjusted we can consider as significant. And we'll also ask for an effect size, because it's useful to report those in many cases. Okay, so let's run that and print out the results, or call the results. So we're seeing the first comparison is time 1 with time 2. We get a t-value of 10.18. If we round that to 2 decimal places, if we use our corrected p-value, we get a p-value that's very small. So it's 2.256745 times e to the negative 0.07. So what that essentially means is we'd move to actually work out what this value was, not in scientific notation like this. We would move this decimal place 7 places kind of to the left essentially. So it gives us a p-value, a corrected p-value of much lower than 0.01. Okay, 0.001, sorry. So it's generally sufficient to specify, when we have a lot of decimals like this, to specify p is less than 0.001. So we've got a significant difference between time 1 and time 2, and we know from our means here that means that pain was significantly higher at time 1 than at time 2. Okay. The next comparison, time 1 with time 3, we've got a t-value of 5.59, and p is 1.997608 times e to the negative 0.04. So same sort of thing, we've got a very small value. We'd have to move this decimal place 4 places to the left. So again, less than 0.001 is probably sufficient to be that precise essentially, and say we have a significant difference between time 1 and time 3. So if we look at our descriptives, so we know that time 1 had a significantly higher mean than time 3 also. The last comparison, time 2 and time 3, we get a t-value of negative 2.40. So that's just a function of which mean was subtracted from which. 2 was, it seems like 3 was subtracted from 2 in this case. We could ignore the negative value and just report the absolute value of this t statistic. And if we look at the Bonferroni corrected p-value, it's 9.218536 times e to the negative 0.02. So we'd move this decimal place 2 places to the left. And what we find there is we get a p-value of about 0.092. So it doesn't reach that threshold of statistical significance. Okay, so I've kind of set out how you might formally report these results below, including reporting the means that we've abstracted from above. So what we can see is that mean pain scores differed significantly between time 1 and time 2, and between time 1 and time 3, but not significantly between time 2 and 3. So time 1 versus time 2, we had t, and then in parentheses we put our degrees of freedom, 14. That's equal to 10.18. P is less than 0.001. Participants experienced significantly more pain at time 1 with a mean of 47.40 than at time 2 with a mean of 34.13. Time 1 versus time 3, t, parentheses 14, degrees of freedom again, equals 5.59. P is less than 0.001. Okay, so participants experienced significantly more pain at time 1, mean equals 47.40 than at time 3, mean is 38.07. Okay, and then the last one, Similar sort of thing, but what we find is we don't get a statistically significant difference. So what we'd say is participants did not experience a significant difference in pain between time 2 and time 3. Okay, and just report the means essentially like that. Right, okay, so that's it. That is the last one-way repeat measures ANOVA example I'm going to conduct. So I've demonstrated a few different ways to do it using a couple of different libraries, SciPy, statsmodels, Pingouin, all really good software libraries. Check out the documentation on those software libraries to see how to do these different things, such as running repeat measures ANOVAs and then conducting the post-hoc tests. Right, okay, I'm going to stop talking now. In the next video, what I'll demonstrate is how to conduct independent groups ANOVA when you need the ANOVA to be robust because you're violating that assumption of homogeneity of variance. I hope this was useful and thank you for listening.